One of the things vectors can be useful for is proving geometrical things, but just proving it in a different way. Keep these sorts of things in mind. When you've got your shape, because obviously if we're doing geometry, it's going to be some sort of shape, triangle, rectangle, whatever it happens to be, then choose a vertex or some other key point in the diagram to represent the origin. So it'd be like with the reference point for all the vectors. Remember, the sum or difference of vectors will create a triangle. Okay, so if you've got a vector u and a vector v, then you can create u minus v by joining head to tail and things like that. Parallel vectors, they're multiples of each other. That multiple might be 1, by the way. But, the angle between vectors we saw yesterday, we can find that using the dot product. And that's useful then because if I want to prove two lines are perpendicular, I can show their dot products equal to 0. And you can always rewrite your vector as a position vector, head minus tail. That idea. Okay, so let's prove a few. We'll start with this one. We're going to prove that the diagonals of a rhombus are perpendicular. Okay, so there's my rhombus. Conveniently, I've labelled one of the vertices O, so what the heck, let's make that the origin. So it's OABC. We know it's a rhombus. Well, we certainly know it's a parallelogram, sorry. So we know it's a parallelogram because those vectors must be parallel. They're telling me it's a rhombus, so I also know that the length of OA is the same as the length of OC. So I'm going to call vector OA A and vector OC C. How creative. Now the diagonals, which we're trying to prove are perpendicular. So one's going to be OB, but that would be the sum of the two vectors. And the other diagonal, AC, is the difference of the two vectors. Now I chose AC, I could have chosen CA, it doesn't really matter. Okay, so let's have a look at the dot products. Remember, we're trying to prove these two lines, or vectors, are perpendicular. So if I can show that their dot products equal to 0, there's my proof, they've got to be perpendicular. So OB times AC. Well, OB we said was the sum, and AC was the difference. And so we've got that difference of 2 squared. So that would be C dot C minus A dot A. But remember, C dot C is the magnitude of C squared, and A dot A is the magnitude of A squared. But recall, this is a rhombus. So the magnitude of C and the magnitude of A are equal. And so therefore, our dot product's equal to 0. And so therefore, we know OB must be perpendicular to AC. Okay, so that was our first one. How about Pythagoras' theorem? Let's prove that. So there's a right angled triangle. I've called the right angle the origin for this one. So OAB. So we want to prove basically the theorem that the square of the hypotenuse is equal to the sum of the square of the other two sides. So let's name some vectors. So the two that are joined up to O, so I'll call one A and one B. So the other one, the hypotenuse, is the difference between the two. So that must be B minus A. Well, let's first of all look at OA squared plus OB squared. So the magnitude of A squared plus the magnitude of B squared. Now AB squared is the hypotenuse, and that's going to be the magnitude of B minus A squared. Well, that is B minus A dot B minus A. So it's using that property in reverse. Normally we'd say, well, A dot A is magnitude of A squared. Well, I'm using that in reverse. Where I'm saying the magnitude of something squared would be that dot that. So B minus A dot B minus A. So B dot B minus 2A dot B plus A dot A. But I know that OA is perpendicular to OB. So A dot B is in fact equal to 0. So therefore, AB squared is B dot B plus A dot A. B dot B is magnitude of B squared plus A dot A, magnitude of A squared, which is what we said OA squared plus OB squared is. So thus we've proven Pythagoras' theorem. Okay, this one's a bit more interesting. Not that the others weren't interesting. So I've got a quadrilateral ABCD. And P, Q, R and S are the midpoints of AC, BD, AD and BC. So if we were to join up P, R, Q and S, what sort of quadrilateral will we get? Now, okay, we could look at our diagram and have a pretty good guess of what we're going to end up with. But let's actually prove it. Now notice this time I didn't conveniently label one O. So I'm going to treat A as the reference point. So all the vectors coming from there. Well, I've got AB, AC and AD. They're all coming from the origin. So I'll call them vectors U, V and W. So now I want to get some, well, the other points. I need to work out what they are. So P is half the vector AC. And we just said the vector AC is V. So it's going to be a half of V. So I've got a coordinate or a point for P. Q is the midpoint of BD. Now we don't have a name for BD yet, so I can go head minus tail. So it'll be half of W minus U. What else we got? R is half of AD. Well, we said AD was W, so it's half of W. Is that all of them? P, Q, R. No, we still got to do S. S is half of BC. So, no, we haven't got a name for BC yet. So again, we'll go head minus tail. So we get half of V minus U. So that should be all our points now referenced. Well, the ones we need anyway. So, PR. If I have a look at PR, head minus tail, so half of V minus half of W, well, I can just factorise that. So PR is a half of V minus W. SQ, again, head minus tail, half of V minus U minus half of W minus U, and we end up with a half of V minus W. The U's end up cancelling, don't they? Yeah. So we get half of V minus W. Hang on a sec. That's the same vector as PR. So we now know that PR and SQ are the same vector. So if they're the same vector, they're both equal and parallel. And you may recall that's one of our proofs of a parallelogram. So it must be a parallelogram. We've got opposite sides that are equal and parallel. So I guess the key with this is pick your reference points, then all of the vectors that are coming from that point, give them a name, U, V, W, whatever you want to call them, and then work out all the other points in the picture, what they would be, and then go from there. Try and show different things. Okay, so 8D, just, not that many, is there? Look, I didn't get you to do 5 or 9. I wonder what they were.